Right now, at this very moment, your body is being penetrated by billions of particles you cannot see, cannot feel, and cannot detect. These particles are passing through your skin, through your organs, through every atom of your being constantly. They've been doing this your entire life, and you've never noticed. Not because you're blind, not because you lack instruments, but because these particles don't interact with light, with electricity, with magnetism, or with the atoms that make up your body. They pass through everything. They are ghosts in the machine of reality. These are dark matter particles, and they outnumber ordinary matter by a ratio of about 5-to-1. For every atom that makes up you, your world, every star and galaxy in the visible universe, there are 5 dark matter particles floating through space. Think about that. 5 times more of something we cannot see than all the visible matter we can. 5 times more of the unknown than the known. 5 times more mystery than certainty. But here's what makes this even more profound. Dark matter isn't alone. There's something else out there. Dark energy. And together, dark matter and dark energy make up 95% of the universe. That means that everything you have ever seen, everything you have ever measured, every star, every galaxy, every atom, every speck of dust, all of it, comprises only 5% of the universe. 95% of reality is hidden from you. We are blind to 95% of what exists. We are navigating a universe in almost total darkness, seeing only the faintest glimmer of light in a vast, incomprehensible void. And yet, we know these invisible components exist. We know their approximate quantities. We can measure their effects. We can see the fingerprints they leave on the visible universe. But we don't know what they are. This is not speculation. This is not philosophy. This is the current state of physics, the deepest crisis in cosmology, the greatest unsolved mystery in science. And what you're about to learn will change how you see reality itself. Before we can understand dark matter, we need to understand how we discovered it. Because this is a story of scientific detective work at its finest. It's a story of observations that didn't match theories, of paradoxes that forced us to confront the limits of our understanding. In the 1930s, an astronomer named Fritz Zwicky was studying a cluster of galaxies called the Coma Cluster. He was trying to calculate the mass of the cluster by measuring how fast the galaxies were moving within it. This is a technique called the virial theorem. It allows you to estimate the total mass of a system based on the velocities of objects within it. Zwicky made his measurements. He calculated the velocities of the galaxies, and then he calculated the total mass required to keep those galaxies orbiting together. The result shocked him. The galaxies were moving far too fast. They were moving fast enough that they should have broken free from the cluster's gravity. According to his calculations, the cluster should have torn itself apart billions of years ago. But it hadn't. The galaxies were still there, orbiting together, held by gravity. There was only one explanation. There had to be far more matter in the cluster than we could see. Matter that didn't emit light. Matter that was invisible. Zwicky called this invisible matter dark matter. But his discovery was largely ignored. For decades, it was considered a curiosity, perhaps even a measurement error. Then, in the 1970s, an astronomer named Vera Rubin made similar observations, but with far more precision and with many more galaxies. She studied the rotation curves of spiral galaxies, how fast the outer regions of galaxies rotate. For a long time, astronomers expected that the outer regions of galaxies would rotate more slowly than the inner regions, just like the outer planets of our solar system orbit more slowly than the inner planets. This is because gravity weakens with distance. But that's not what Rubin found. The outer regions of galaxies rotated at roughly the same speed as the inner regions. This was impossible according to the laws of gravity and the mass we could see. Unless, once again, there was far more matter than we could see. Rubin's observations were meticulously careful. Her data was undeniable. And slowly, the scientific community began to accept it. Dark matter was real. It had to be. By the 1990s, the evidence became overwhelming. Multiple independent lines of evidence all pointed to the same conclusion. Dark matter made up the vast majority of the matter in the universe. We learned to map it. We learned to measure its gravitational effects. We learned to calculate its distribution. And we learned that galaxies are embedded in massive halos of dark matter, like fruit floating in a vast, invisible cloud. But there was one problem. Despite decades of searching, despite increasingly sophisticated experiments, we could not actually detect dark matter particles directly. We could only see their gravitational effects. It was as if the universe was hiding something from us. Something fundamental. Something that governed the structure of everything we could see. And the deeper we looked, the more we realized how little we actually understood. So what is dark matter? If we can't detect it directly, what can we say about it? The leading theory is that dark matter is made of weakly interacting massive particles, or WIMPs. These are hypothetical particles that barely interact with ordinary matter or light, but do have gravity. WIMPs would have been created in the early universe, in the Big Bang itself, and they would exist in vast numbers, far more numerous than ordinary atoms. As the universe expanded and cooled, ordinary matter clumped together to form the first stars and galaxies. But dark matter was there too, providing the gravitational scaffolding that made this structure formation possible. Without dark matter, galaxies would never have formed. The universe would be smooth and uniform. There would be no stars, no planets, no life. Dark matter, in a very real sense, is the reason you exist. But WIMPs are just one hypothesis. There are others. Some scientists propose that dark matter consists of axions, hypothetical particles even more ghostly than WIMPs. Axions would be produced in vast quantities in the early universe and would barely interact with anything. Others propose primordial black holes. Black holes formed in the early universe from density fluctuations in the Big Bang itself. These would be dark matter made of collapsed matter. Still others propose that dark matter exists in extra dimensions. It would share gravity with our universe, but otherwise remain completely separate, like a parallel reality touching ours through gravitational force alone. The truth is, we don't know. And that's the profound mystery at the heart of physics today. For 40 years, scientists have been searching for direct detection of dark matter particles. Experiments buried deep underground, shielded from cosmic rays, with detectors so sensitive they can pick up a single atom collision. And despite all this effort, we have found nothing. Not one confirmed detection of a dark matter particle. Nothing. This is beginning to suggest something profound. Either dark matter is far more elusive than we thought, existing in a way that makes it almost impossible to detect directly, or our understanding of what dark matter is might be fundamentally wrong. Some physicists are now proposing radical alternatives. Perhaps dark matter isn't made of particles at all. Perhaps it's something else entirely. Perhaps it's a modification of gravity itself on cosmic scales. Perhaps it's extra dimensions. Perhaps it's something we haven't even imagined yet. The mystery deepens with every experiment that comes up empty. Let me paint you a picture of what the universe looks like if we could somehow see dark matter. What would it look like if we could suddenly make the invisible visible? First, imagine the visible universe as we know it. Stars, galaxies, clusters of galaxies, spreading out across billions of light years. This is what we see with our telescopes. This is the universe we know and study. Now, imagine overlaying this with dark matter. Imagine being able to see the vast, invisible scaffolding that supports all this visible structure. You would see massive, sprawling halos of dark matter surrounding every galaxy. These halos are enormous, sometimes extending hundreds of thousands of light years from the galactic center. And they are far more massive than the visible galaxies they surround. You would see even larger structures, dark matter filaments connecting clusters of galaxies. These filaments are like the cosmic web, the large-scale structure of the universe. They form the highways, along which ordinary matter flows and collects. You would see vast voids between these filaments, regions containing very little matter, either dark or ordinary. These voids can be billions of light years across, and you would see the very densest concentrations of dark matter surrounding massive galaxy clusters. The gravity here is so intense it warps space-time, bending light from distant galaxies into multiple images, creating what's called gravitational lensing. This is the true structure of the universe. This is what's really out there. The visible universe is like the foam on the surface of the ocean, while the vast, dark ocean itself lies beneath, unseen and invisible. And this dark matter structure is dynamic. It's not static. It swirls and flows. It collides with itself. It concentrates and disperses. And embedded within it, like creatures in a vast, dark sea, are galaxies and clusters of galaxies, riding the currents of dark matter. This is the universe we actually live in. A universe dominated by something we don't understand. But here's something even more disturbing. Dark matter might not be alone in its invisibility. And that's where we get to dark energy. Dark energy is, if possible, even more mysterious than dark matter. At least dark matter interacts gravitationally in ways we can measure and predict. Dark energy does something we find almost incomprehensible. It makes the universe expand faster and faster. In the 1990s, astronomers studying distant supernovae made a shocking discovery. The universe's expansion is accelerating. For billions of years, the expansion was slowing down due to gravity. But about 6 billion years ago, something changed. The expansion began to speed up. This was unexpected. It violated every prediction physicists had made. It suggested that something was pushing the universe apart, working against gravity, accelerating the expansion. We don't know what this is. We call it dark energy. It comprises about 68% of the universe. Think about that. 68% of the universe is made of something we have absolutely no idea what it is. Something that appears to have negative pressure, pushing everything apart. Something that becomes more dominant as the universe expands and matter becomes more dilute. One hypothesis is that dark energy is the vacuum energy of spacetime itself. Spacetime, according to quantum mechanics, isn't empty. It's seething with virtual particles constantly being created and annihilated. This creates a kind of zero-point energy that permeates all of space. And this energy has gravity-like properties that make it repulsive rather than attractive. Another hypothesis is that dark energy is a field that permeates all of spacetime, similar to electromagnetic fields, but with properties we don't understand. Or perhaps we're wrong about gravity itself on cosmic scales. Perhaps general relativity breaks down, and what we interpret as dark energy is actually a modification of gravity that only shows up at the largest scales. The truth is, we don't know. And this is even more profound than dark matter, because at least we have some theories about dark matter. With dark energy, we're grasping in the dark. Together, dark matter and dark energy make up 95% of the universe. And we understand neither of them. We are living in profound ignorance. We are navigating a cosmos we barely comprehend. So what are the implications of this? What does it mean that 95% of the universe is hidden from us? First, it means that everything we know about the universe, all our measurements, all our theories, all our understanding, is based on studying only 5% of what's actually there. We are trying to understand the universe by looking at the foam and not the ocean. It's as if we were studying human anatomy by only looking at the hair on the surface of the skin, while ignoring all the internal organs, the blood vessels, the bones, the nervous system. We would get a fundamentally incomplete picture. Second, it means that the universe is far more complex than we think. If dark matter has any internal structure, if it has any interactions beyond gravity, if it has any properties we haven't discovered yet, then we're missing entire branches of physics. There might be dark matter-particle interactions we haven't observed. There might be dark matter events happening all around us that we can't detect. There might be dark matter physics that would revolutionize our understanding of the universe. Third, it means that the future of cosmology and physics lies in solving these mysteries. Dark matter and dark energy are not peripheral concerns. They are central to understanding reality itself. For the next generation of physicists, for the next era of scientific research, the big questions will be about the invisible universe. What is dark matter made of? What is dark energy? How do they interact? What other hidden components might exist? Fourth, and perhaps most profoundly, it means we need to be humble. We thought we understood the universe. We built theories, made predictions, confirmed them with observations. We thought we were close to a complete understanding of physics, but we were studying only 5% of reality. And that should make us question everything. How many other fundamental misconceptions are we making? How many other pieces of the puzzle are we missing? The universe is humbling us. It's telling us that there is far more to discover than we ever imagined. Now, let's talk about some of the specific mysteries and paradoxes surrounding dark matter, because the story gets even stranger. One major mystery is the distribution of dark matter. We've learned to map it using gravitational lensing and other techniques. And what we find is unexpected. Some galaxies have more dark matter than we'd expect based on models. Some have less. The relationship between the amount of ordinary matter and dark matter varies from galaxy to galaxy in ways we don't fully understand. There's something called the core cusp problem. Our models predict that dark matter should be denser toward the centers of galaxies, forming a cusp, a sharp peak in density. But observations often show a core, a region of relatively uniform density at the center. This suggests our models of dark matter are wrong, or that there's something else going on. There's the missing satellites problem. Our simulations suggest that large galaxies should be surrounded by hundreds of small satellite galaxies. but we observe far fewer than our models predict. Where are the missing satellites? Are they there but too faint to see? Or is our understanding of dark matter wrong? There's the too big to fail problem. Some of our brightest satellite galaxies should be orbiting much farther away if our models are correct. But they're close to the main galaxy. This suggests that either dark matter behaves differently than we think, or there's additional physics we haven't accounted for. And then there's the question of dark matter streams. As the Milky Way travels through space, it should be surrounded by streams of dark matter particles. Some of these streams might be remnants of smaller dark matter clumps that were torn apart by the Milky Way's gravity as it passed through them. If we could detect these streams, we might be able to learn more about dark matter's properties. But we haven't found them yet. Either they're too small to detect, or they don't exist, suggesting our models are wrong. Every observation raises new questions. Every data point seems to contradict our theories. And we're no closer to understanding what dark matter actually is. Let's imagine, for a moment, what would happen if dark matter suddenly vanished. If, in an instant, all the dark matter in the universe disappeared. First, galaxies would become unstable. The dark matter halos that surround them, providing the gravitational glue that holds them together, would be gone. The stars in the outer regions of galaxies, moving too fast to be held by the gravity of the visible matter alone, would escape into space. Galaxies would fly apart. The Milky Way, containing roughly 100 to 200 billion stars, would be torn to shreds. Stars would stream away into the void, no longer held by gravity. Some would collide with one another. Most would escape, leaving the Milky Way as a dying remnant of what it once was. And this would happen to every galaxy in the universe. Every single one. The cosmic web of structure would collapse. Galaxy clusters would disperse. The large-scale structure of the universe, held together by dark matter, would unravel. It would take time, millions of years, for the effects to fully play out. But within a few million years, the universe would be unrecognizable. No longer a cosmos of galaxies and clusters, but rather a chaotic sea of individual stars, planets, and debris, scattered randomly through space. Life, dependent on the stability of stars and planetary systems, would face a cataclysm. Most intelligent civilizations would be destroyed. The universe would become a far colder, darker, lonelier place. All because of something we can't see. Something that makes up 85% of all matter in the universe. This is the profound realization. The fate of galaxies, the structure of the universe, the possibility of life itself, all of it depends on a substance we don't understand. We are not masters of the universe. We are passengers, and we're riding on something we know almost nothing about. So where are we in the search for dark matter? What's being done to solve this mystery? There are multiple experimental approaches ongoing right now. Underground detectors, shielded from cosmic rays, are trying to catch dark matter particles as they pass through Earth. These experiments have become increasingly sensitive, able to detect a collision with a single atom. But so far, they've found nothing conclusive. Large particle accelerators like the Large Hadron Collider are trying to create dark matter particles in high-energy collisions. If we can create them, we might learn about their properties. But again, nothing yet. Telescopic observations are mapping dark matter with increasing precision using gravitational lensing. We're learning more about its distribution and structure, but we still don't know what it is. Some scientists are proposing alternatives to particle-based dark matter. Perhaps dark matter is really a modification of gravity. Perhaps general relativity is wrong on cosmic scales. Perhaps we need to revise our understanding of how gravity works. Others are proposing exotic alternatives. Dark matter in extra dimensions, primordial black holes, cosmic strings, or other exotic objects. And some are proposing that dark matter might actually consist of multiple different types of particles or phenomena. Perhaps what we call dark matter is really several different things we're lumping together under one name. The search continues. It's one of the most active areas of research in physics today. Billions of dollars are being spent. Thousands of scientists are working on it. And yet, we're no closer to a definitive answer. It's as if the universe is deliberately hiding from us. It's as if reality is protecting its secrets. But we keep searching. Because the alternative, to give up and accept that 85% of the universe will remain forever unknown, is unthinkable. Let me tell you about one of the most disturbing implications of dark matter's existence. Something that keeps physicists awake at night. If dark matter exists, and if it really does have the properties we think it does, then the universe might be far more alive with activity than we ever imagined. Dark matter particles are constantly colliding with one another. Billions are passing through your body right now. When they collide, some of them might annihilate, converting their mass to energy in a burst of radiation. This process is happening everywhere in the universe, all the time, completely invisible to us. In the densest regions of dark matter, in the hearts of galaxies, in the cores of galaxy clusters, dark matter annihilation might be a significant source of energy. We might be seeing the effects of this in observations of high-energy radiation from galactic centers. But there's something even more disturbing. What if dark matter has more complex interactions than we think? What if, under the right conditions, dark matter particles can interact with one another in ways we haven't considered? Some physicists have speculated about dark life, hypothetical beings or processes that might exist in the dark matter universe. If dark matter has enough complexity, if it can form structures and interact in sophisticated ways, could it give rise to something like life, but composed entirely of dark matter? This sounds like science fiction, and it is, but it's also a logical extrapolation of what we know. If ordinary matter, which comprises only 5% of the universe, can give rise to conscious, intelligent life, why couldn't dark matter, which comprises 85% of matter, do something similar? Such beings, if they existed, would be completely invisible to us. They would live in the dark matter universe, interpenetrating our universe without us ever knowing. They could be aware of us through gravitational effects, but we would be completely unaware of them. We would be blind to them, and they might be everywhere. I'm not saying dark matter life definitely exists. The conditions required might be too extreme, or dark matter might be too simple. But it's a possibility we can't rule out given our current knowledge. And it points to a profound truth. The universe is almost certainly far stranger and more complex than our 5% visibility allows us to perceive. There might be physics we haven't discovered. There might be phenomena we can't even imagine. There might be entire layers of reality operating just beyond our ability to detect. And all of it is hidden. All of it is dark. Let's talk about the future of dark matter research. Where are we headed? What might we discover? In the coming decades, new telescopes and experiments will come online. The Vera Rubin Observatory will map dark matter distribution with unprecedented precision. Next-generation underground detectors will achieve sensitivities far beyond current experiments. New particle accelerators might create dark matter particles. Some scientists are proposing radical new approaches, using quantum computers to search for dark matter signatures in existing data, using gravitational wave detectors to sense dark matter interactions, using space-based telescopes to observe dark matter halos directly through the radiation they might emit. And some are proposing we need to completely rethink our approach. Instead of trying to detect dark matter particles, maybe we should focus on understanding the large-scale effects. Maybe we should use the universe itself as a laboratory, studying how dark matter shapes galaxies and the cosmic web. One possibility that many physicists think is likely: we'll discover that dark matter is more complex than we thought. It might not be a single type of particle. It might be multiple particles with different properties. It might have internal structure. It might have interactions we haven't considered. Another possibility: we'll discover that dark matter does interact with ordinary matter in subtle ways. We might find evidence of dark matter reactions, dark matter chemistry, even dark matter biology. A third possibility: we'll discover that gravity itself is different than we think. General relativity might be modified on certain scales. Dark matter might not exist at all. What we interpret as dark matter effects might be a misunderstanding of how gravity actually works. And a fourth possibility, perhaps the most unsettling: we'll discover we can't solve this. We'll find that dark matter is fundamentally unobservable using any technique we can devise. It will remain forever hidden, a permanent mystery at the heart of physics. If that happens, it will force us to accept that there are limits to human knowledge. There are aspects of reality that science might never fully understand. We will have to live with profound ignorance at the foundation of our understanding of the universe. And perhaps, in a strange way, that's fitting. The universe showing us that we are not meant to know everything, that there are mysteries that exist to remind us of our smallness, our limitation, our humility. Now, I want to take a step back and talk about the philosophical implications of dark matter. Because this isn't just a physics problem. It's a fundamental question about reality and our place in it. For most of human history, we thought we could, in principle, understand the universe. We developed sciences and philosophies based on the assumption that reality is knowable, that with enough observation and thought, we could understand everything. The Enlightenment was built on this. The scientific revolution was built on this. The idea that the universe is a rational place, governed by laws we can discover and understand. But dark matter challenges this assumption. It says, there is a fundamental component of reality that you cannot directly observe. You can see its effects, but not the thing itself. And you might never know what it really is. This is a kind of epistemic humility, a recognition that knowledge has limits, that there are aspects of reality that might be forever beyond our reach. Some philosophers call this the veil of ignorance. We are beings with limited senses and limited instruments. We perceive only a tiny fraction of the electromagnetic spectrum. We can't see radio waves or infrared or ultraviolet without instruments. We can't perceive gravity directly. We can't perceive subatomic particles without particle detectors. And now we're discovering that there's an entire universe of matter we can't perceive even with our best instruments. It's passing through us right now. It's holding galaxies together. It's the dominant form of matter in the universe. And we can't see it. What other aspects of reality are we missing? What other invisible forces or particles or phenomena are operating right now, completely undetectable to us? This is unsettling, because it suggests that our understanding of reality is fundamentally incomplete. Not just incomplete in the sense that we don't know everything, but incomplete in the sense that we're missing entire categories of phenomena. We are like creatures at the bottom of the ocean, seeing the faintest light filtering down from the surface, completely unaware of the vast world that exists above the water. We think we understand the ocean because we can study the rocks and creatures near the bottom, but we're blind to the sky, the land, the universe beyond. And perhaps, somewhere far above us, other civilizations are looking down, studying the light from distant galaxies, completely unaware that we exist down here in the dark matter depths. Dark matter is a humbling force. It forces us to acknowledge the limits of human perception and understanding. It forces us to accept that we are not the center of reality, that we are not privy to all of existence, that we are, in a very real sense, blind. But it also fills me with a sense of wonder. Because if we're blind to 85% of matter in the universe, what else might exist that we haven't discovered? What other marvels, what other phenomena, what other ways of existing might be out there, hidden from our eyes? The universe is infinitely richer and stranger than we realize. And dark matter is just the beginning of understanding how profound that strangeness really is. Let me paint you one final picture. A vision of the dark universe beneath the visible one. Imagine you could somehow leave your body and float up above Earth. You could see the planet below you, rotating in space, the sunlight glinting off oceans and ice. You could see the moon, orbiting nearby. You could see the sun, radiating light and heat. Now imagine that you could suddenly see dark matter. The entire Earth would be surrounded by a massive halo of dark matter, extending far into space. The dark matter halo would be far larger and more massive than Earth itself, extending hundreds of thousands of miles into space. You could see dark matter flowing around the Earth, pulled by Earth's gravity, but also spread out into a vast cloud. You could see it swirling and churning, individual particles colliding and bouncing off one another. Now zoom out further. You can see the entire solar system. The sun, surrounded by a dark matter halo. The planets orbiting within it. The entire solar system embedded in a dark matter cocoon. Zoom out further still. You can see the entire Milky Way galaxy. A disk of hundreds of billions of stars, spiraling outward from a central bulge. But surrounding it all, like an invisible ocean, is a massive halo of dark matter. The halo is so large that the visible disk of stars looks tiny by comparison. Like a handful of sand on an infinite beach. Zoom out even further. You can see the local group of galaxies, the Milky Way, Andromeda, and dozens of smaller galaxies. And between them, surrounding them, interpenetrating them, is dark matter. Vast flows of invisible substance that bind these galaxies together. Zoom out to the cosmic scale. Now you see the entire observable universe. A cosmos of billions of galaxies, stretching across 93 billion light years. It's breathtaking, beautiful, incomprehensibly vast. But this is only what you can see. The visible universe. The 5% that emits light. The 95% that doesn't. It's all around you. A vast, dark ocean of dark matter and dark energy. The visible universe is like the foam on the surface of this ocean. Beautiful, intricate, complex. But only the foam. The real universe, the true cosmos, is something far stranger, far deeper, far more incomprehensible. And we're just now beginning to understand that it exists. We live in a universe of shadows. We are creatures that see only the briefest glimmer of light in a vast darkness. We have built our science, our understanding, our entire perception of reality on this thin slice of visibility. But the universe is far more than we see. It is far more complex, far more vast, far more mysterious. Dark matter reminds us of this. It is a cosmic wake-up call, a message from the universe saying, "You don't know what you think you know. There is far more here than you can perceive. There are mysteries within mysteries. There are depths you haven't fathomed. And that's okay, because the search for understanding is what drives us forward. The mysteries are what inspire wonder. The unknown is what calls us to explore, to discover, to push the boundaries of knowledge." The fact that 85% of the universe is hidden doesn't make us smaller. It makes us more insignificant in one sense, but more alive with the possibility of discovery in another. We are at the beginning of understanding our universe. The real beginning. We've only just started to ask the right questions, and the answers might reshape everything we know about reality itself. This is the mystery of dark matter. This is the invisible universe, and we're only just beginning to see it. We've been searching for dark matter particles for 4 decades. For decades of experiments, each one more sophisticated than the last. And in all that time, we found almost nothing. This is frustrating for physicists. We're used to solving problems. We're used to building experiments that confirm or refute theories. But dark matter has been different. Dark matter has been elusive. Dark matter has been silent. Let me walk you through some of the major experiments that are trying to detect dark matter right now. The XENON experiment is one of the most sensitive. It's located deep underground in Gran Sasso, Italy, more than a kilometer below the surface. This depth is crucial because it shields the detector from cosmic rays, which would create false signals. The XENON detector is a large tank filled with liquid xenon, a noble gas cooled to -95 degrees Celsius. If a dark matter particle happens to collide with a xenon nucleus, it would create a tiny flash of light and a small ionization signal. The detectors are so sensitive that they can pick up a collision with a single atom. But in all the years XENON has been running, it has found no confirmed dark matter signals. It has set increasingly stringent limits on what dark matter particles can be. It has ruled out certain types of WIMPs with certain masses and interaction strengths. But it hasn't found dark matter. The LUX experiment, located in South Dakota, has done the same. Incredibly sensitive, deeply underground, and also finding nothing. The Super CDMS experiment, using a different detection principle based on the cooling of crystals when dark matter particles collide with them, has also found nothing. And there are dozens more. Pico, Xenon 10, Xenon 100, Xenon 1T Darwin. Each generation more sensitive. Each one coming up empty. This is beginning to worry physicists. Not because we think dark matter doesn't exist, the gravitational evidence for it is overwhelming. But because the fact that we haven't found it after 40 years of searching is starting to suggest that either. Dark matter particles interact even more weakly with ordinary matter than we thought. They're even more ghostly, even more elusive, which would make them even harder to detect in the future. 2. Our assumptions about what dark matter is might be wrong. Maybe it's not WIMPs. Maybe it's something else entirely. Maybe it's not particles at all. 3. Dark matter might exist in a form that is fundamentally impossible for us to detect directly. It might be in extra dimensions. It might be in a parallel universe that only touches ours through gravity. It might be something we haven't even conceived of. The null results are becoming as significant as the results we might find. They're telling us that dark matter is not what we expected. But the search continues, and new experiments are coming online that might finally break through. The next generation of detectors will be even more sensitive. They'll cover larger volumes. They'll use different detection principles. Some will be sensitive to different types of dark matter particles that current experiments can't detect. And some scientists are proposing that we need to think differently. Instead of looking for individual particle collisions, maybe we should look for the statistical effects of billions of dark matter particles passing through detectors. Maybe we should look for subtle changes in atomic nuclei caused by dark matter interactions. Maybe we should use quantum computers to search for dark matter signatures in the noise of existing experiments. Maybe we should use gravitational wave detectors to sense the disturbances caused by dark matter interactions. The search is evolving. And while we haven't found dark matter yet, the hunt itself is revealing profound things about the universe. It's teaching us that reality is stranger than we imagined, and that sometimes what we don't find is just as important as what we do. Not all physicists believe that dark matter is made of particles, and there's a good reason for that skepticism. After 40 years of searching with increasingly sophisticated experiments, we've found nothing. Some scientists are proposing radical alternatives. The most famous of these is called MOND, Modified Newtonian Dynamics. MOND proposes that gravity itself doesn't work the way Newton described it. It proposes that on the very largest scales, when gravitational acceleration becomes extremely small, gravity behaves differently. The basic idea is simple. Newton's law of gravity, which works perfectly for our solar system and even for galaxies, might break down on the largest scales. Instead of gravity always being proportional to mass divided by distance squared, perhaps at very large scales or very small accelerations, gravity changes its behavior. If this is true, then we wouldn't need dark matter to explain why galaxies rotate too fast. The galaxies would rotate the way they do because gravity itself is different than we thought. MOND can explain many of the observations that dark matter explains. It can explain galaxy rotation curves. It can explain why galaxy clusters seem to have more mass than visible matter suggests. But MOND has problems too. It's difficult to make MOND work on all scales. It has trouble explaining the cosmic microwave background. It struggles with gravitational lensing observations. And it requires adding extra mathematical complexity to gravity, which physicists are reluctant to do unless absolutely necessary. So while MOND is interesting, most physicists don't think it's the complete answer. There are other modified gravity theories. TeVis, tensor vector scalar theory, tries to make MOND consistent with relativity. There's Einstein ether theory. There's varying constants theory. There's scalar tensor theory. All of these propose that gravity, or some other fundamental force, works differently than we currently understand. The problem with all of these is the same. They're complicated. They require adding extra mathematical structures to our theories of physics. And physicists have a principle called Occam's razor, which suggests that the simplest explanation is usually correct. Dark matter, despite being mysterious, is simpler conceptually than modifying gravity itself. Dark matter says, there's more matter out there than we can see. Modified gravity says, the rules of gravity are different than we thought. The first seems simpler, but the second might be true. This is the uncertainty we're in. We have multiple theories. Some propose dark matter particles. Some propose modified gravity. Some propose both. And we don't yet have enough evidence to definitively rule any of them out. This is actually exciting from a scientific perspective. It means there's still mystery. It means there's still discovery to be made. It means we're at a frontier. But it's also frustrating, because it means we don't have a clear path forward. We're groping in the dark, trying to understand what the darkness is made of. And the darkness keeps its secrets. Without dark matter, you would not exist. This is not hyperbole. This is a literal statement about the physics of the universe. In the early universe, only a few 100 million years after the Big Bang, the first galaxies began to form. But they didn't form the way you might expect. Gravity alone, acting on the ordinary matter in the early universe, would have been too weak to assemble galaxies quickly. The densest regions would have collapsed slowly, gradually accumulating more and more matter. It would have taken far longer than the age of the universe for galaxies to form. But they did form. We see them in the data from the James Webb Space Telescope. Fully formed galaxies with billions of stars, existing less than 1 billion years after the Big Bang. This rapid formation is only possible because of dark matter. Here's how it works. Dark matter was not uniformly distributed in the early universe. There were regions with slightly higher densities and regions with slightly lower densities. These density fluctuations came from quantum fluctuations in the earliest moments after the Big Bang. These dark matter overdensities created gravitational wells, regions of stronger gravity. Ordinary matter was pulled toward these wells. But the ordinary matter, unlike dark matter, could interact with itself. It could collide. It could lose energy. It could cool and collapse. So the dark matter created the gravitational scaffolding. And the ordinary matter, responding to this scaffolding, rapidly collapsed inward, forming dense clumps that would eventually become galaxies. Without the dark matter wells, the ordinary matter would have collapsed much more slowly. There wouldn't have been enough time for the first galaxies to form. But with dark matter, the ordinary matter had a blueprint to follow. The dark matter showed it where to go, and galaxies formed rapidly. This process repeated on all scales. Dark matter halos formed around galaxy clusters. Smaller dark matter halos formed around individual galaxies. The entire cosmic web of structure was sculpted by dark matter gravity. We can see this in computer simulations. When physicists simulate the early universe, including dark matter, galaxies form as expected. We see the right distribution of galaxy sizes. We see the right clustering patterns. We see structures that match observations. But when physicists remove dark matter from the simulations, when they simulate the universe with only ordinary matter and no dark matter, nothing forms properly. The universe remains too smooth. Galaxies form much too slowly. The universe looks nothing like what we observe. This is powerful evidence that dark matter really does exist and really does play this crucial role in galaxy formation. And it means that every star, every planet, every atom that makes up every person, everything that exists in visible form, owes its existence to dark matter. You are made of matter that was shaped by dark matter gravity. You exist because dark matter created the gravitational scaffolding that allowed ordinary matter to collapse into the structure we see today. In a very real sense, dark matter is your cosmic parent. It created the conditions for your existence. And you'll never directly perceive it. You'll never see it or touch it or feel it. But it's there. It's always been there. And it's as essential to your existence as the oxygen in the air you breathe. This is the profound connection between the visible and the invisible, between what we can see and what remains forever hidden. Dark matter is not separate from us. It is woven into the very fabric of our existence. There's a hypothesis that's gaining traction among theoretical physicists. It's called the hidden sector hypothesis. The basic idea is this: dark matter might not be a single simple particle. Instead, it might be an entire sector of physics, an entire collection of particles and forces that exists parallel to the particles and forces we're familiar with. Just as ordinary matter is governed by the electromagnetic force, the weak nuclear force, and the strong nuclear force, perhaps dark matter is governed by its own set of forces. These forces would be completely separate from the forces we know. Dark matter particles would interact with each other through these dark forces. They might form dark atoms, dark molecules, even dark chemistry. They might have dark light, particles that transmit force among dark matter particles, analogous to photons for ordinary matter. If this is true, then dark matter wouldn't just be a simple component of the universe. It would be an entire parallel universe of physics, existing alongside our universe, interpenetrating it, but completely invisible to us except through gravitational effects. This is mind-bending. It means that right now, dark matter particles are colliding with each other in your vicinity, interacting through dark forces, perhaps even forming complex structures. All of this is happening completely invisibly to you. In the densest regions of the universe, near black holes, at the centers of galaxies, in the cores of galaxy clusters, dark matter interactions might be intense. Dark matter particles might be annihilating, creating bursts of dark radiation. Dark matter structures might be forming and breaking apart. It would be like having a completely different universe occupying the same space as ours, but visible only through gravity. Some physicists have speculated about dark matter stars, objects made of dark matter, held together by dark matter gravity, perhaps radiating dark light. These objects would be completely invisible, but they would have gravitational effects that we might potentially detect. Others have speculated about dark matter black holes made of dark matter, perhaps formed in the early universe. These would be gravitationally indistinguishable from black holes made of ordinary matter, but they would have no ordinary matter event horizon. And some have even speculated about dark matter life, complex structures in the dark matter universe that might, in some abstract sense, be considered alive. Structures that self-replicate, that process information, that respond to their environment. This is highly speculative, but it's a logical extrapolation of the idea that dark matter is not just a simple particle, but an entire sector of physics. If true, it would mean that the universe is far richer and more complex than we currently imagine. It would mean that visible matter, atoms, stars, galaxies, life, is just the tip of the iceberg. The vast majority of activity in the universe might be happening in the dark matter realm, completely invisible to us. We would be like blind creatures in a sighted world, unable to perceive the vast complexity around us. And perhaps that's humbling. Perhaps that's the point. The The universe is showing us that we are not privy to all of its secrets. There are realms of existence we may never fully understand. Part 6. Dark Matter in Extra Dimensions. One of the most fascinating possibilities is that dark matter doesn't exist in our three spatial dimensions at all. It exists in extra dimensions. This might sound like science fiction, but it's based on serious physics. In string theory and other extensions of the standard model of particle physics, there are additional spatial dimensions beyond the three we're familiar with. These extra dimensions are supposed to be very small, so small that we can't see them directly. But they exist. Now imagine that dark matter particles live in these extra dimensions. They would move through their own 4, 5, 6, or more dimensional spaces, completely invisible to us. But gravity, according to string theory, and these higher dimensional models, can propagate through all dimensions. So even though dark matter particles are confined to extra dimensions, they would still have gravitational effects in our three-dimensional universe. This would explain why we can't detect dark matter directly. It's not in our three-dimensional space. It's somewhere else, somewhere we can't reach or observe directly. But its gravity leaks into our space. It shapes galaxies and galaxy clusters. It holds the universe together. This is a profound idea. It suggests that there are entire universes, entire spaces of physical reality, existing alongside our own, occupying the same location in space, but extending in directions we can't perceive. If true, it would mean that dark matter is not just invisible. It's dimensionally inaccessible. We would never be able to directly observe it, no matter how sensitive our instruments became, because it exists in a place we simply cannot go. Some physicists have proposed ways to test this. If dark matter exists in extra dimensions, then dark matter particles might occasionally interact with ordinary matter in higher dimensional effects. These interactions might show up as slight deviations in particle physics experiments. The Large Hadron Collider has been searching for such deviations. So far, nothing definitive has been found. But the search continues. And if this idea is correct, then dark matter is not just invisible. It's geometrically hidden. It exists in a place that is, in a fundamental sense, inaccessible to our three-dimensional perspective. This is truly humbling. It means that no matter how advanced our technology becomes, we might never be able to directly access the majority of matter in the universe. We would be forever prisoners of three dimensions, able to perceive only the effects of higher dimensional reality, but never able to fully comprehend it. And perhaps that's as it should be. Perhaps the universe is designed to keep some mysteries forever beyond our reach. Part 7. The Future of Dark Matter Research. We're entering a new era of dark matter research. New telescopes, new detectors, and new theoretical frameworks are coming online that might finally shed light on this darkness. The Vera Rubin Observatory, which will begin operations in the coming years, will map the distribution of dark matter across the entire sky with unprecedented precision. Using gravitational lensing and other techniques, it will create a detailed map of where dark matter is located. It will reveal the large-scale structure of dark matter distribution in the universe. This might reveal patterns that current observations miss. It might show us that dark matter has structure we don't yet understand. It might reveal concentrations or voids or flows that provide clues to dark matter's nature. Next-generation underground detectors are being built that will be thousands of times more sensitive than current experiments. These will be able to detect dark matter particles if they have the properties we think they might have. And some of these detectors will use new detection principles. Instead of looking for individual particle collisions, they'll look for the subtle effects of dark matter streaming through the detector. They'll look for the annual modulation signal, the fact that Earth's velocity relative to the dark matter halo changes as it orbits the Sun, so the flux of dark matter particles should vary seasonally. This modulation has never been definitively detected, but it's being searched for, and if found, it would be smoking gun evidence for dark matter particle existence. Space-based telescopes are being planned that will observe the universe in wavelengths sensitive to dark matter radiation. If dark matter particles annihilate, they produce gamma rays and other radiation. Observing this radiation could tell us about dark matter density and distribution. Gravitational wave detectors are improving, and as they do, they're becoming sensitive to subtle gravitational wave signals. Some of these signals might come from dark matter interactions or dark matter objects, and theoretical physicists are exploring new models. Axionic dark matter, sterile neutrinos, Q balls, non-relativistic Goldstone bosons. The menagerie of possible dark matter candidates is growing. Some physicists are proposing that we should look for dark matter indirectly, by looking for the effects it has on ordinary matter in subtle ways that haven't been explored yet. Others are proposing that we should abandon the particle physics approach altogether. Maybe dark matter isn't about particles. Maybe we should focus on understanding the large-scale gravitational effects, and see if that leads us to dark matter's nature. The future is wide open, and that's exciting, because it means we're on the cusp of a great discovery, or perhaps a great revolution in physics, where we realize that dark matter is something we never expected. One way or another, we're getting closer to understanding the 85% of reality that has been hidden from us for so long. Part 8, the cosmic perspective and the limits of knowledge. Let me bring you back to where we started. With that disturbing image, 85% of the matter in the universe is invisible to you. It's passing through your body right now. It's holding galaxies together. It's shaping the large-scale structure of the cosmos. And you don't know what it is. What does this mean? What should we make of this profound mystery at the heart of physics? I think it means several things. First, it means that our understanding of the universe is incomplete. Not just incomplete in the sense that we don't know all the details, but incomplete in a fundamental way. We're missing a major component of reality. Imagine if you were studying human anatomy, and you could only see the skin and hair. You could see all the external features. You could measure them precisely. You could develop theories about how the skin works. But you would have no idea about the organs inside, about the bones, the blood, the nervous system. Your anatomy would be 95% unknown to you. And your theories about how the body works would be based on understanding only 5% of what's actually there. That's where we are with physics. We understand ordinary matter and the forces that act on it. We've developed precise theories. We've built technologies based on these theories. But we're blind to 95% of the matter in the universe. Our theories are built on a 5% foundation, and that should concern us. It should make us question whether our entire framework for understanding the universe is correct. Second, it means that there are limits to what we can know. Or at least, there might be limits. Dark matter might be fundamentally unobservable. The universe might be designed such that certain aspects of reality are forever hidden from us. This is philosophically significant. For centuries, science has been based on the idea that reality is knowable, that with the right instruments and the right approach, we can understand everything. But dark matter suggests otherwise. It suggests that there are aspects of reality that are beyond our reach, that no matter how advanced our technology becomes, we might never fully understand what dark matter is. If this is true, then there are permanent limitations to human knowledge. There will always be mysteries that remain unsolved. Third, it means that we are insignificant. Not insignificant in the cosmic size sense. We knew we were small compared to galaxies and the universe. But insignificant in the sense that we are blind to the vast majority of what exists. We like to think of ourselves as observers of the universe, as scientists who are slowly uncovering its secrets. But in reality, we're fumbling in the dark, able to see only the faintest glimmer of the true cosmos. We are prisoners of our perceptions, blind to what matters most, blind to what holds the universe together. And yet, fourth, this should fill us with wonder. Not despair, wonder. Because if 85% of the universe is hidden, what does that mean about the possibilities? What does it mean about the nature of reality? What does it mean about what might exist out there, beyond our perception? The universe is far stranger and more complex than our limited understanding suggests. There are phenomena we haven't imagined. There are forms of matter we haven't conceived of. There might be entire realms of physics operating at scales and in ways we haven't explored. We are at the very beginning of understanding the universe. We've only just lifted a corner of the veil. There are infinite mysteries waiting to be discovered. And that is thrilling. That is what should motivate us. The knowledge that we are blind, but that we might be able to learn to see. The dark matter mystery is not a problem to be solved and forgotten. It's a cosmic koan. It's the universe asking us the deepest questions. What do you really know? How certain are you in your understanding? Are you prepared to have everything you think you know challenged and overturned? The answer to all three questions should be, I know far less than I think. I'm less certain than I should be. And yes, I'm prepared to be wrong. Dark matter is the universe's way of keeping us humble. It's a constant reminder that we are small, that we are limited, that we are seeking truth in darkness. But the seeking itself is what matters. The search itself is what makes us human. The willingness to face the unknown and try to understand it. Dark matter will yield its secrets eventually. We don't know when. We don't know how. But we will keep searching. Because that's what we do. We are creatures of curiosity. We are driven to understand. And no matter how vast the darkness, no matter how hidden the reality, we will persist. We will shine our light into the void. And gradually, slowly, we will learn to see what has been hidden. This is the future of dark matter research. And it is the future of human understanding itself. Conclusion. We began this journey with a disturbing image. 85% of the matter in the universe is invisible to you. It's passing through your body right now. You are immersed in it, surrounded by it, composed of matter shaped by it. But you cannot see it. And after all we've explored, the history of dark matter discovery, the experiments searching for it, the alternative theories, the role it plays in galaxy formation, the possibility of a hidden sector, the idea of extra-dimensional dark matter, the future of research, we end at the same place. We don't know what it is, but we know it's there. And that knowledge changes everything. It changes how we understand the universe. It changes how we understand ourselves. It changes the questions we ask and the answers we seek. Dark matter is the greatest mystery in physics. It's the cosmic invitation to discover something truly revolutionary. It's the universe showing us that there is far more to reality than we can perceive. And that is the message I want to leave you with. The universe is vast. The universe is mysterious. The universe is far stranger than you imagine. And we are only just beginning to understand it. Thank you for this journey through the darkness. Thank you for exploring the invisible universe with me. The mystery continues. The search goes on. And somewhere out there, in the depths of dark matter's hidden realm, the answers are waiting. We just have to learn to see.